Today we're going to finish chapter number 5, and we're going to look at the lecture number 3 of chapter number 5, and in our study of looking at applications of Newton's first and second law. The learning objective for today: apply Newton's second law on a body moving along a circular path. Now, we're going to look at things that move around circular track. Now, in chapter number 3, we looked at circular motion as a way of two-dimensional motion. And I told you it's wrong to say that an object moves around a circle with constant velocity, because a velocity is a vector. And if you want to go around the circle, you have to change your direction. So we said the right way is you say that you can go around the circle with constant speed, because you can keep the magnitude of your velocity constant, but you're going to change the direction of your velocity. And we said that this is what we call uniform circular motion. And we talked about two acceleration when you go around the circular motion. We said that a rad, which should equal to v squared over r, and we said this is working toward the center of the circle, and it is responsible for changing the magnitude, changing the direction of your velocity. And this is what we call a rad. And then we said there is another, which we call a tangential, and we said this is responsible for changing the magnitude of your velocity. So in the case of uniform circular motion, you don't have this one. You only have the a rad. You're going around with constant speed. But in the case of non-uniform circular motion, you also include the a tangential. Today we're just going to consider uniform circular motion, but that doesn't mean you can extend that to non-uniform circular motion as well. So in the case when you move around the circle with constant speed, this is what we call uniform circular motion. And of course there will be a force, and this net force will be directed toward the center. And you know, in accordance with Newton's second law, we said the summation of the force is equal to ma, or we say that the net force is equal to ma. So in the case when the net acceleration is toward the center, you only have uniform circular motion. That means you're going to have an acceleration which is equal to v squared over r, and the magnitude of that of the a radial or a centripetal is v squared over r. So in that case, your net force along the radius will be equal to mv squared over r. So these are the cases. So if you look at the diagram here, just to make things clear, you see the green arrow here, and the green arrow here is always tangent to the circle. And you can see it has the same length. That means the same magnitude. That means it is moving with constant speed. Then you can see the orange here, which is the direction of the acceleration, which basically directed toward the center of the circle. And with this, of course, you can have a net force, and the net force will be directed toward the center of the circle, and it's equal to mv squared over r. So we're only considering the case when the net force is directed toward the center of a circular path or circular track, and so on. Now the cases that we're going to consider here to keep things going around a circle, you can basically use a tension. Like in the case what you have here, you have a mass, and the mass is tied to a rope or a cable or a wire, whatever it is, and you force it to go around a circle where basically that's where you're pulling here at the center. Now, you can also make cars go on roundabouts or curved paths, and you're forcing them to go along a circular track. And this is the cause of this will be static friction force. Now, you can go on a vertical circle, and when you're dealing with a vertical circle, like a roller coaster here, what keeps you going around the track? And in this case, we'll talk about the normal force. Now, we want to illustrate a point here, and I think we dealt with that in chapter number 3 as well. Your velocity is always tangent to the circular path. And the question that we have here, what if the string breaks? So you're tying a mass with a string, and you whirl it around to go in a circular path. Now, what happens if you break this one? As soon as this breaks, then there is no force pulling the mass toward the center. And the mass is free to move on its own now. And if it breaks here, you will find that it's moving straight in this direction here. Now, if that happens for a mass here, and it will be moving that way if you break the string here. If you bring it, let's say here, and you break, it will be moving that way. And that's why we say here, what happens if the string breaks? We say that no net force acts on the ball, so it obeys Newton's first law and moves in a straight line at constant velocity. And that's why we tell you that the velocity is always tangent to the circular track. So it will be moving this way or that way or that way and so on. But what keeps the object moves around a circle is a net force toward the center, and I told you that this will give us a net acceleration which is equal to v squared over r, which we call the centripetal acceleration. So let's take an example here to illustrate this, and the example that we're going to pick here is force in uniform circular motion. A sled with mass 25 kg rests on horizontal sheet of ice. Ice, that means you don't have friction, so we say frictionless here, is kept in a uniform circular motion. So it is uniform. Uniform, that means constant speed, by a rope of length 5 meters. If the sled moves 5 complete revolutions every minute. So they did not give us the speed, but they told us that it's 5 revolutions every minute. So what we are given here, we're given the mass, which is 25 kg. We're given the radius, which is 5 meters. And we are given that it makes 5 revolutions in 1 minute. So this is what we're given here. And they're telling us that there is a rope which pulls toward the center, and it's an ice, so there is no friction, and the sled can move around. And they ask us about the force that the tension exerts, and that's what they want from us here in this problem. So what you can do is, if you follow your free body diagram, the weight will be down, the normal force will be up, and then you have a net force which is acting toward the center. Now, in a situation like this, if you want to talk about X and Y axis, maybe we can talk about horizontal and vertical axis. V here, I don't mean velocity, but it could be vertical. You can Say that this is y, this is x, whenever you like, but the force is always pointing toward the center. So if I pick it here, my horizontal will be this way. If I pick it here, my horizontal will be this way, and so on. So here you will see that your tension is pointing toward the center of the circle. And of course, the weight and the normal force are, the weight is usually down toward the center of the earth. The normal force is vertical to the supporting surface. So in this case, you will have a net force, and that net force will equal to MA rad, which will be equal to MV squared over R. So that's my net force along the radius. But what forces do I have along the radius? I only have the tension. So if I look at the summation here, the only force that I have is the tension, and this tension should equal to mv squared over r. Now m is given, r is given. They did not give me v, but they told me 5 revolutions per minute. Now 5 revolution, a revolution means you go around the circle one complete time, one complete circle. And you know, a circumference of the circle, it's 2 pi r. So I can get my speed by saying it's equal to 5 times 2 pi r. That will give me the distance for 5 revolutions. And 1 minute contains 60 seconds. And this will give me a speed of 2.62 meters per second. So to calculate the tension, it will be 25 times 2.62 squared over 5. And this gives you 34.2 newtons. And now you've calculated the tension that we have in the rope that makes the sled go 5 revolutions in 60 minutes. Now, if you increase the tension, that means you're going to increase the speed. But you have to be careful. Every cable, every wire has a certain strength. When it reaches that, it may break. So we always have to be careful with how much speed we can go to. Is this clear? Any question on this one? In this example here, we're going to cause circular motion, but with a tension that is not being applied along the center of the circle, but component of it will be there. And we talk here about a conical pendulum. Now, you're all familiar with a cone. If you go and buy ice cream, you can always buy cones of ice cream, and you can basically put a scoop or 2 scoops on top of it. So that's the shape of a cone. Now, a pendulum, usually you take a rope and you tie a mass to it, and you bring it up, and it will basically start going back and forth. That's what a pendulum is. In this situation here, okay, what we're doing is basically tying the mass with a rope of length L, but it's not swinging back and forth. It's caused to go around in a circle. So if you look at it, it will give you the shape of a cone, and that's why you call it conical pendulum here. A bob of mass M at the end of wire length L moves in horizontal circle of radius R with constant speed. Find the tension F in the wire and the period T. Usually in pendulums, you want to find the period. So what's the period in this case here? Now, the same thing that you can do here, you can basically take your weight down. You don't have a normal force because there is no supporting surface here, and then you'll have a tension which would be basically pulling this way. Now, I told you in this case, you will choose a horizontal and a vertical. So the vertical will be this way. So the weight will be along the vertical. The tension makes an angle here. So it will have a horizontal component and a vertical component. Now this angle here is beta, simple geometry, and you all know that. This angle here is going to also equal to beta. So your tension here makes an angle beta with the vertical. So if you take components, this will have one component going this way, which will be T cosine beta, and it will have a component going that way, which will be T sine beta. Now they ask us here to find the force. Okay. So what we're saying here, we're looking at, after we do our free body diagram, so the weight is down. Instead of the tension, we put a force because that's what we can apply. So it will have a vertical component. In this case, we called it Fy. And it will have an horizontal component. We chose it to be Fx here, but I told you the right way is horizontal and vertical. So when we look at the forces along the y, there is no motion up and down. So it's equal to 0. And the only forces that you see here, it is, if you want to do that, you will say it is the Fy minus W should equal to 0, which indicate that the Fy should equal to W. And that's what we have here. We say the Y component of the force, or the tension in this case, should equal to the weight. And I told you that should equal to T cosine beta. We say here if cosine beta is equal to mg, so the F here will equal to mg divided by cosine beta. And now we obtained the tension. Then they ask us about the period. Now we look at the horizontal circle. And we know that the net force is acting toward the center of that horizontal circle, and it should equal to mv squared over r. So what are the forces that are acting toward the center? Well, it will be the tension sine beta, which is F sine beta here. And F sine beta should equal to mv squared over r. Now, the pendulum is always of length L. So if you look at the radius here, it will be L sine beta. That's your radius. Now, if you want to get your speed, it will be 2 pi r over t. It's the circumference, like what we did in the previous example, divided by the period t. That's what I'm interested in. So now I know that this should equal to mv squared over r. So the m I have, the v squared will be 2 pi, and the r will be L sine beta over t squared. And of course, I have to divide by r, which is L sine beta. So F sine beta, which is the x component of the tension, it's going to equal to m. R is L sine beta, and this squared will be 4 pi squared over t squared, L squared sine beta squared. You can cancel this with the square. So you'll have mg sine beta over cosine beta equal to 4 pi squared over t squared ml sine beta. You know that sine beta over cosine beta is tan beta. So you have mg tan beta equal to 4 pi squared over t squared ml sine beta. You can cancel the m. I'm interested in t here. So I can take 1 over in both sides. So 1 over here will give me 1 over g tan beta. 1 over here will give me t squared goes to the top. And then at the bottom, I will have, or in the denominator, I'll have 4 pi squared 1 over L sine beta. Now I'm interested in t, so I'll take t squared. I can multiply this to the other side. So t squared will equal to 4 pi squared L sine beta over g tan beta. So t squared will equal to 4 pi squared L over g sine beta. I can now take tan beta, and it's equal to sine beta over cosine beta. You can cancel the sine with the sine. Of course, the cosine will go to the top here. So if you take t, which is square root of t squared, will give you square root of 4 pi squared is 2 pi square root of L cosine beta over g. And now this is the period of the conical pendulum here. So you got your force and you got the period t. Is this clear? Is this clear? Any question on this? Now we'll deal with the other example where you want to go around a circular flat curve, and they ask us here a car rounds a flat unbanked curve with radius r. The coefficient of static friction between the tires and the road is mu s. What its maximum speed? Again, you can come here and you can basically choose your horizontal and you choose your vertical, okay? And your horizontal in this case always pointing toward the center. So the weight is down, the normal force is up, and it's going around a circle of radius r. It's a flat. Now I want to see what keeps this car going around. Well, the car could slide this way or that way, but what is keeping the car on the track? There must be something that's doing that. And what's keeping the car on the track is the attraction between the tires and the road. And this attraction is coming from friction. In this case, it is static friction. So the static friction is causing the car to go on the circular track. So in the vertical, I have normal and weight. On the horizontal, I have the static friction. And you all know when we talked about static friction in the last lecture, we said static friction is less than or equal to mu s times the normal force. But there is a maximum value for the static friction. After that, that's it. You lose it. And the car starts moving. So that's what we have here. If we lose that static friction, the car will be sliding. And it cannot be kept on the circular track. So the maximum static friction that we can have, it will be the mu s times the normal force. So now, if I look at my net force along the circle or the horizontal circle, well, it should equal to mv squared over r. But the only force that's working toward the center and keeping the car on the track is the static friction force. And that should equal to mv squared over r. Now they asked me about the maximum speed. And whenever you increase your speed, the static friction will increase. But there is a point when you reach the maximum, and that's it. You lose that attraction. And that's why we said that when we achieve the maximum static friction, we will get the maximum speed that we can go around the circular track. Now, you know that the maximum friction is equal to the mu s times the normal force. So we want to know what the normal force is. Now, you know that if you look at the vertical component here, it will be the normal force minus W equal to 0 because the car is not moving up and down. So the normal force will equal to the weight. So we say that the mu s times the weight should equal to mv squared, v max squared divided by r. You know that the weight in this case is equal to mg. So mu s mg is equal to m v max squared over r. You can cancel the m from both sides. So you have your maximum v max over r is equal to mu s r. You can multiply it out. So from here you will have the mu s g r should equal to the v max squared. So if you want to get your v max, it will be the square root of mu s r g, and that's the maximum speed that you can achieve. You cannot go higher than this. If you go higher, that means that's the maximum static friction, and the car is going to slide and cannot be kept going around the circular track. Now, if you, for example, take a roundabout where the radius is about 20 meters, and we'll take a mu s of 1, which should be the maximum for rubber on the street. You do that, you'll get about 14 meters per second, which is 50.4 kilometers per hour. And in Al-Ain here we have lots of roundabouts, and that's why they tell you you do not exceed this speed in the roundabout, because the car will slide if you do that. Imagine if there is rain and you have oil and things like that, the static friction is going to be very less, and you really have to be cautious and careful when you go in roundabouts. Now, in order to achieve higher speeds, you cannot do anything about the g. The only thing that you can change is the radius and the mu s. Mu s, usually you know that the type of the material. Remember, we always talked about the material. So you have rubber. You can do as much as you can with rubber, and of course you have asphalt underneath. So you cannot do much with mu s there. The only thing that you can do is r. You can make r bigger and bigger, and that's why in streets inside the city, roundabouts are not that big. If you look at major streets, like highways, and there is a roundabout in the way, you always find it very big. That means you can enter or you move at higher speeds. Now, one thing that you have to be careful with here, static friction is a friend in this case. It's keeping the car from going sideways. But some of you may think of why the car is moving forward. Yes, you need a friction. It's like walking. When you walk, if you're walking on ice or oil, you find yourself, you're basically slipping and you cannot walk. But the attraction between your shoes and the road makes it easier for you to walk. And that's basically friction, static friction, that's causing this. Now, in the case if you're just looking at the car moving in the forward direction, well, we're not going to deal with this here, but you may deal with it later in other courses, maybe something that we call rolling friction. So I don't want you to think of the static friction that we have here. It's basically for moving the car in the forward direction. I'm talking about sideways. Why do we keep the car on the track from sliding? And the source for that is the attraction between the tires and the street or the road. And as I explained here, it could dictate the maximum speeds that you can have. So you have to be careful, especially when the beginning of the summer, the oil may basically in the asphalt, maybe on the top, and then you have rain or water, and that could make it very slippery. So your coefficient of static friction will be very low. So you have to be careful in these situations. Is this clear? Any question on this? Now, can we improve on this. Now, on highways, sometimes you are forced to turn because of the terrain that around you. You have sand, or you have things that make you go around, so you have to turn. So you're going to go on a curve. And usually on the highways, you have a high speed. And again, we're talking here about to keep yourself on the track. You don't want to slide off the road. And we said the static friction basically keeps you on the track. But we can add another factor that can help. And in this case, we basically talk about banked curve. So you see a car here, and that's a highway. You basically bank it at an angle, so it may look like an incline, and this can help you going around the track. So we're not going to deal with the static friction here. It should be done in full, but we're only going to look at the effect of the bankment here, how much you bank your curve. So again, if you do your free body diagram here, the weight is down, the normal force is up. Now, if you're talking about friction, friction should be basically going this way, but I told you we're going to ignore friction now. And you're going around the circle, the radius is here. So if you pick, this is the horizontal, this will be the vertical here. The weight is along the vertical, but the normal force makes an angle now. So this normal force here will have a horizontal component and it will have a vertical component and horizontal component. The horizontal component basically works toward the center of the circle, and that can basically be part of the net force that's working toward the center of the circle. Now we can include the friction as well here, and the friction also will have two components, but we're going to leave it for now. So if I look at the angle that this normal force makes, and I can look at the angle that it either makes with the vertical or the horizontal. Well, this angle here, it's going to be 90 minus beta. If this angle here is beta, and if you extend this all the way, you know that this angle should be 90, but this angle here is going to be 90 minus beta. So your x component, which will be the vertical, the y component, which will be vertical here, it will be n sine 90 minus beta. And the horizontal component here will be n cosine 90 minus beta. So if I look along the vertical, and the car is not moving vertically, so it's the net force is equal to 0. So it is the vertical component of the net of the normal force minus the weight should equal to 0. But because the angle here will be 90 minus beta, so the vertical component will be n sine 90 minus beta minus W should equal to 0. That's why we say here that n sine 90 minus beta is equal to the weight. You know that complementary angles, right? Sine 30 equals cosine 60. So here, sine 90 minus beta is equivalent to cosine beta. So that's why we say n cosine beta should equal to mg, where mg is the weight. That's if we look vertical. Now, if we look at the horizontal part, and here I don't want you to think along the incline. You're thinking about the center of the circle here. And along the center of the circle, you should have the net force equal to mv squared over r. And along the circle now, we consider the horizontal component of the weight, and that should equal to n cosine 90 minus beta should equal to mv squared over r. You know cosine 90 minus beta is equal to sine beta. That's why we have n sine beta equals to mv squared over r. And that's your second equation here. Now, if I divide 2 by 1, that means n sine theta equals mv over squared. I divide it by 1. So you'll have n sine beta divided by n cosine beta. N and n will cancel out. And sine beta over cosine beta will give you tan beta. And here you will have mv squared over r over mg. You can cancel the m. And you get v squared over rg. So tan beta here will equal to v squared over g. You can also say you can get your v from here, which would be the square root of r g tan beta. Now we're only looking at the effect of the angle here. If you want to do this in full, you also have to include in the static friction, and you will take horizontal and vertical component of the static friction, and you will have to deal with two cases. One case, the car doesn't slide down, and the other case, the car will not slide up. So you'll have a minimum speed and maximum speed. But the idea here is to show you the effect of the angle at which we bank the curve. So here, for example, if you want to go with the speed of 36 kilometers per hour, which is about 10 meters per second, in a radius of 20 meters, well, you actually, tan beta will equal 10 squared over 29 times 9.8, and that will give you an angle of 26.5 degrees. Now, the problem here, we're just showing you the effect of when you bank the curve. Of course, you have to add in the effect of static friction as well. But we did not, for simplicity here, we just want to show you this effect. That's why in highways, you always have high speeds. And when you are forced to turn, they always bank the curve to make sure that you can actually go at comfortable speeds. Now, if they don't bank it, and they make the radius very small, this will be basically a case for accidents. And they really have to put a sign, okay, telling you that you have to be careful. Or you may actually end up with bad engineering. Okay. So that's the idea here of looking at circular motion. And I always told you, always look at toward the center of the circle. Is this clear? Any question on this? Now let's look at uniform circular motion in a vertical circle, and that could be many cases, like an airplane, a pilot doing a loop, a roller coaster, like what you have here. Okay. So what happens in this case? Now you always in a seat. So the idea here, to make sure that you're not going to fall down, you're on the top, the seat, you are basically, you feel the seat pushing on you. If the seat is not pushing on you, you're going to fall down. And they tell you here to do it at two locations. You do it at the bottom and at the top. So let's look at these two situations. Remember, the force or the net force is going toward the center of the circle. So always the net force will equal to mv squared over r. Now if you look at the top, and the top you will have the weight down. You're sitting on a seat, and the seat basically is pushing you up with a normal force. Now in this case here, and we say vertical, or you can say y. you have two choices. You can say that the positive is up. So in this case, you'll say the normal force minus the weight should equal to, but the net force is working toward the center. So you say minus v squared over r. Or you can say, no, I will take the positive down along the circle. So if you do that, you will have the weight down, which is basically toward the center. We take it positive, minus the normal force up. And that should equal to mv squared over r, because that's the net force toward the circle. It will work even if you want to consider that case. You will get the same equation. The weight is equal to mg minus the normal force is equal to mv squared over r. So if I want to get the normal force here, it will equal to mg minus v squared over r. So you can take the m as a common factor. So it will be g minus v squared over r. And this is, of course, less than the weight. So if your v squared over r equals g, well, that means the normal force is going to be equal to 0. So usually when they do that, they have to make sure that you have speeds where you cannot fly off the seat. Now, when you look at the case when you are at the bottom, it is basically the net force is equal to mv squared over r. The weight is down, the normal force coming from the seat is up. So normal minus weight equal to mv squared over r. So the normal force here will equal the weight plus mv squared over r. So it's mg plus v over, and this is greater than the mg. So if you're designing a seat, well, you said you can, no, you make the seat in such a way that the seat can support your weight, which is mg. But in the case when you are basically doing this and you're going around in a circular motion with a speed, then you have to consider this factor as well here. And that becomes important if it's an aeroplane. In an aeroplane, especially fighter airplanes, they do loops and sometimes at higher speeds. So the seat has to, especially if loop and he comes or the pilot comes to the bottom, has to be strong enough to support the weight. And that's the importance of this circular motion. Is this clear? Any question on this? So we looked at circular motion when the case it is horizontal or vertical, but we can consider it as two-dimensional motion here as well. And the force that works toward the center of the circle, which is equal to v squared over r. Good. Let's try to deal with some discussions here. I mean, we can look at this is the pendulum that we did. So attached to a ceiling by a thin wire of length L, the bob moves at constant speed in a horizontal circle of radius R, with the wire making a constant angle beta with the vertical, the tension in the wire. And they give you this option. Greater than mg, equal mg, less than equal mg, it depends. So we already worked that one out in the examples, and we said that the tension should equal to mg over cosine beta. And you know that cosine beta is less than 1, which makes the F greater than mg. So in that case, the tension is going to be greater than mg. So we can follow up and what we did in the previous example, and we can also ask more questions. Now in this situation here, you have a pendulum. This is not a conical pendulum. This is a normal pendulum, where you're going to raise it up to a point and then you let go, so it will be start swinging back and forth. They tell you a pendulum of length L, the mass swings back and forth at the lowest point of its motion, which is point Q here. The tension is equal 3/2, which is 1.5 mg. What is the speed of the pop at this point here? When we deal with energy, we'll do this later as well, but let's look at it in terms of forces here. You have the tension pulling up, weight is down, and the net force is toward the center here, and the radius will be the length of the pendulum here. So the net force should equal to mv squared over r. T minus the weight should equal to mv squared over r. You know that the weight is equal to mg, so your tension, they tell you it's 3/2 mg. So 3/2 mg minus mg equals to mv squared over r. You cancel the m. 1.5 minus 1 will give you half. So half of g is equal to v squared over r. So your v will equal to square root of r g over 2. But your r here is going to be the length of your wire. So v is equal to 1/2 lg, and that's why we say that the right answer here is D. So that's how you reason in dealing with problems of this sort. So what we dealt with is basically uniform circular motion here. Now in this situation here, in this case here, we only picked the point Q, but the speeds here will be varying. Okay, but we'll deal with that case when we deal with energy, potential and kinetic energy and so on. But they gave you one case. So the tension here, it's not going to always equal this value. You have to remember that. It's going to be different because the speeds will be different here. So that's one thing that you have to keep in mind. But they gave you 1 point. Okay. So in circular motion, when it's uniform circular motion, we actually look at the net force pointing toward the center, and the net force to the center is equal to mv squared over r. Now, non-uniform circular motion, that means your v is not going to be constant. But you can always pick points on the circle, and you can say the net force toward the circle is equal to mv squared over r. You may actually have a tangential acceleration, and then you have a tangential force as well, and then you have to combine them. But in this case, we only wanted to illustrate that also in circular motion, you have to look at a net force toward the center of the circle, which is equal to mv squared over r. Is this clear? Is this clear? I want to bring to your attention something about Newton's law of universal gravitation, where you have two masses, m1 and m2. There is a force of a gravity between the two, and the magnitude here is equal to g m1 m2 over r squared, where F is the force between the two masses, g is what we call the gravitational constant. It's equal to 6.674 times 10 to the minus 11 meter cube kg to the power minus 1. That means per kilogram second squared. M1 is the first mass, M2 is the second mass. R is measured from the centers. Okay, so we basically go from the center here to the center there. Okay, that's how you measure things. And this is the force of gravity between any two objects. Now, in your when we are on the surface of the Earth here, and you feel the effects of gravity, the Earth, by the way, has a big radius. You're talking about a radius which is about, roughly speaking, 6.38 times 10 to the 6 meters. That's a huge radius. So if you look at things on the surface of the Earth, it does not have a very big mass. Okay, so even if you want to measure the distance between here and here, you want to take it from the center to the center, you will find that more or less you're talking about the radius of the arc of the Earth. So if you look at the force, you will see G, mass of the Earth, mass of the object, divided by the distance between the two centers. Most likely we're going to take it as the radius of the Earth squared. If you something is 1 meter or 2 meters or 100 meters, it does not compare to 6.38 times 10 to the 6 meters. Now, GME over RE squared, that's what G is equal to. So it's like when we say mg, that's the G here. So the G here on the surface of the Earth, if we approximate that the Earth to be a nice sphere and that's the average radius, there are small variation from this, but that to good approximation, this is the case here. So G is equal to 6.67 times 4 times 10 to the minus 11. Mass of the Earth is huge, is approximately 5.98 times 10 to the 4 kilograms. The radius is 6.38 times 10 to the 6 meters. And of course, you have to square that. That will give you roughly about 9.8 meters per second squared. And in kinematics, we assume that the G is constant near the surface of the Earth. If you go higher or lower, more or less, you're going to have this value here. And sometimes they may give you 9.1. Okay. Okay, so this is basically what the value of G is. Now, this brings in an interesting point because we have lots of satellites orbiting the Earth. So how fast these satellites are orbiting the Earth? Now, you know that if you look along the, if you have here the Earth, and then you want to put around a satellite, so how fast is this satellite orbiting the Earth? Now, you know what is, and you can say that the satellite is h above the Earth. Satellite usually doesn't have, we go from the center, but usually they're very small. So in accordance with universal gravitational law, so you say G, mass of the Earth, mass of the satellite, divided by how far is the satellite from taken center to the center. So it will be the radius, you have to include the radius of the Earth here. So it will be the radius of the Earth plus how high the satellite above squared. That should equal to m, because along the center you have the net force, which is equal to mv squared over r. So it's ms v squared r e plus h, and that's basically the distance between the satellite and the center of the Earth. You can cancel that with the square. So you'll have, and you cancel the ms with the ms, so you have a g me over r e plus h. So your v here will equal to a g m of the Earth r of the Earth plus h, and that can give you high speeds. Now you may play around with this. Let's say if I want the satellite always facing the same point on the Earth, you know that the Earth rotates on its axis, so you want to know the speed of this, how the speed of the point on the Earth, of how it's rotating, and you can make what we call synchronization, okay, where you can basically make it at a height where the satellite is always going to be facing the same point on the Earth. So that's just something to give you the effect of circular motion here and how you can position satellites and so on around the Earth. Is this clear? Any question on these? And also about the G. So if you go higher above the surface of the Earth, the G will basically become lower and lower. Maybe we can touch upon this later when we talk about energy and we talk about escape velocity and things like that. Okay. but satellites are basically going around the Earth with high speeds. Is this clear? Any question on this? So, in summary, we only touched upon uniform circular motion, and we said you always have a centripetal acceleration or radial acceleration, which is equal to v squared over r, and this works toward the center of the circle, and that will give you a net force along this center of the circle, which is equal to ma rad, which will be m v squared over r, and you can apply in Newton's second law for this circular motion as well. Okay. Is this clear? Any questions on this? Any questions on this? Good.